Welcome to Norton Chemistry. Today we're going to be revising the entire Module 3 in under 1 hour. Get your periodic table ready, as you'll need it as we go through the video. Elements are arranged in order of increasing atomic number in the periodic table. Elements are in periods, which are the rows in the periodic table, and groups, which are the columns of the table. Elements in the same group have similar physical and chemical properties, because they have the same number of outer shell electrons. And the definition of periodicity is the regular repeating patterns of atomic, physical and chemical properties with increasing atomic number. And we can split up the periodic table into the S, P, D and F blocks, which are based on the orbital which the highest energy electron is located in. So I've coloured in each block of the periodic table. So to the left you have the S block. Elements in the S block have the outer shell electrons in the S subshell. You've got the D block in the middle. In the D block elements, the outer shell electrons are located in the D subshell. You've got the P block on the right and the F block at the bottom. Ionization energy measures the energy required to remove electrons from atoms, forming positive ions. So the first ionization energy definition, and this is one you need to remember, is the energy required to remove one electron from each atom in 1 mole of the gaseous element to form 1 mole of gaseous 1+ ions. So for example, the first ionization energy of aluminium we represent using this equation. 1 mole of gaseous aluminium forms 1 mole of gaseous aluminium 1+ ions, and an electron is removed. So we've got a question. Write the equation for the first ionization energy of oxygen. Include state symbols. Never forget to use state symbols when you're writing the equations for ionization energy. So for oxygen, we're going to have a gaseous atom of oxygen going to oxygen 1+ gaseous and losing an electron. Successive ionization energies apply to the removal of electrons after the first ionization energy. So for example, the second ionization energy is when Al1+ goes to Al2+ and you lose an electron. Then the third ionization energy is when Al2+ goes to Al3+ and you form another electron, and so on and so forth. So the trends in successive ionization energies provide evidence for electron shells, so provide evidence for the number of shells and the number of electrons each holds. Within each shell, successive ionization energies increase slightly, as the outer shell is pulled slightly closer to the nucleus as electrons are removed. Between shells, there are larger increases, also known as jumps, in ionization energies, as the electron is removed from a lower energy shell, which is much closer to the nucleus. So for example, we have the first, second, third and fourth ionization energies of aluminium. And you can see that from the first to the second, we have a relatively small jump. From the second to the third, we have another relatively small jump. And then from the third to the fourth, we have a very large jump, a very large increase, as the electrons begin to be removed from the lower energy shell. And you can see this represented in a diagram. So in the aluminium atom, we have 3 shells, and as these 3 electrons are removed from this outer shell, we then start to remove from the second energy level. So once we've removed 3 electrons, then for the fourth ionization energy, we have to remove another electron to remove 4 electrons, and that requires a much larger energy than before because the electrons are so much closer to the nucleus, so there's a much greater nuclear attraction to the electrons. So there are certain factors affecting ionization energies, and I like to remember them using the mnemonic SCAR, but you also need to add an A at the end so it becomes SCARA, but that essentially stands for shielding, charge, atomic radius and attraction. So shielding, or electron shielding, depends on the number of shells. So the lower the number of shells, the lower the electron shielding. Less shielding means greater nuclear attraction. And then we have charge, or nuclear charge. So the greater the number of protons in the nucleus, remember protons are positive, the greater the nuclear charge. Greater charge means greater nuclear attraction to the electrons in the outer shell. Then we have atomic radius. So the greater the number of shells and the smaller the nuclear charge, the greater the atomic radius is. So a smaller radius leads to a greater nuclear attraction because the outer shell electrons are closer to the nucleus. So attraction, the greater the nuclear attraction, the more energy is required to remove an outer shell electron. Therefore, the ionization energy will be greater. So ionization energy is essentially a measure of the nuclear attraction to the outer shell electrons. So periodic trends, shielding remains the same across periods and increases down groups as new energy levels are added. So across a period, there's no new energy levels added, there's no new shells, so the shielding remains the same. Nuclear charge increases across periods as new protons are added to the nucleus, and it increases down groups. However, this increase is outweighed by the increase in atomic radius as new shells are added. And then we have atomic radius, which decreases across periods because the outer shell is pulled closer as the nuclear charge increases. So as protons are added to the nuclear attraction to the outer shell increases, and the nucleus can then pull the outer shell in closer, and therefore the outer electrons become closer to the nucleus. And then it increases down groups as new energy levels are added. And then we have some periodic trends in ionization energies as well. So across periods, the ionization energy actually increases because shielding stays the same, the nuclear charge increases, and the atomic radius decreases. So the nuclear attraction to the outer electrons increases. And then down groups, ionization energies decrease because shielding and atomic radius increases. So that outweighs the increase in nuclear charge. So the nuclear attraction to the outer shell electrons decreases. Here we've got a graph that represents the periodic trends in ionization energies. As we go across the period from hydrogen to helium, the ionization energy increases. Then as we go down a group to lithium from helium, the ionization energy decreases rapidly as a new energy level is added, and therefore shielding and atomic radius increases, which decreases the nuclear attraction to the outer shell electrons very quickly. Then across the period we can see that from lithium to neon, the ionization energy increases again, but from helium to neon, it's not very well represented on the graph, but we should see a decrease in the ionization energy because we're going down the group, and we know that down groups ionization energies decrease. Now you can see that I've circled the anomalies, so we'll talk about those in a bit, but essentially there are some small anomalies in the trend of ionization energies increasing across periods, which is to do with electron configurations, so I'll explain that in a second. So the anomalies are from group 2 to group 3, so for example from beryllium to boron, ionization energy actually decreases slightly as the electrons begin to be removed from the p subshell rather than the s subshell. So the p subshell is higher energy than the s subshell, so the outer electrons are actually further from the nucleus, leading to less nuclear attraction. So less energy is required to remove those electrons. And you can see I've represented that diagrammatically at the top right hand corner. Beryllium has 2 electrons in the 2s subshell and has no electrons in the p subshell. And boron has 2 electrons in the 2s subshell and 1 electron in the 2p subshell. And the 2p subshell is higher energy, so it's further from the nucleus. So there's less nuclear attraction, which leads to this slight anomaly, but then the trend increases afterwards. And then there's also a slight anomaly from group 5 to group 6, so for example nitrogen to oxygen. And the ionization energy decreases slightly because the electrons begin to pair in the p subshell. So paired electrons actually repel each other. So if you remember back to electron configurations, the definition of an orbital is an area of an atom that holds up to 2 electrons of opposite spin. So those electrons spin in opposite directions because electrons are both negatively charged, so they repel each other, and this decreases the energy required to remove the outer electron. And we need to remember that orbitals fill singly first, then they pair. So each orbital in the 2p subshell fills singly and there's no pairing of electrons, whereas in oxygen, you can see in the diagram, we have pairing of electrons in the orbital in the 2p subshell, and that pairing makes it easier for the atom to lose electrons and form a positive ion. Then we have some periodic trends in bonding and structure. So across period 2 and period 3, the trending melting point relates to the bonding and structure. The melting point increases from group 1 to group 4 because the elements have giant structures, so metallic first and then covalent. The melting points decrease from group 4 to 5 because the structure goes from giant to simple molecular, which is only held together by weak intermolecular forces, which require much less energy to overcome than covalent bonds. So you can see that represented on this graph. So you've got the giant structures. So in group 1, 2, 3 and 4, there's a trend of increasing melting points as we go from metallic bonding to covalent bonding. And then from carbon to nitrogen, the melting point rapidly decreases as we go to a simple molecular structure because intermolecular forces, and especially London forces, require much less energy to overcome than strong covalent bonds. So we've got some exam questions. Feel free to have a go and then I'll explain the answer. The trend in the first and second ionization energies of group 2 elements can be linked to the increase in chemical reactivity down the group. The first and second ionization energies of calcium and strontium are given in the table. So we can see that they both have a similar first ionization energy, and the second ionization energy of calcium is slightly larger than the second ionization energy of strontium. Write an equation, including state symbols, to represent the second ionization energy of strontium. The definition of the second ionization energy is the energy required to remove 1 mole of electrons from 1 mole of gaseous 1 plus ions to form 1 mole of gaseous 2 plus ions. So we need to go from gaseous strontium 1 plus to gaseous strontium 2 plus, and we need to lose 1 electron to go from 1 plus to 2 plus. Then we're being asked to explain why the first ionization energy of strontium is less than the first ionization energy of calcium. So if we look at the periodic table, we can see that strontium is lower than calcium. And remember, the ionization energies decrease down groups. And then we want to use our mnemonic SCAR or SCARA to help us explain this difference. So if we're going down a group, we're adding an extra energy level. So electron shielding increases, and then the nuclear charge is going to increase, but it's going to be outweighed by the increase in atomic radius. It increases as a new energy level is added. And then this leads to the nuclear attraction in strontium to the outer shell electrons being less than the nuclear attraction in calcium to the outer shell electrons. And this will mean that less energy is required to remove 1 mole of those electrons. So the properties of group 2, which are the alkaline earth metals, they all have 2 electrons in their outer shell, so in the S subshell, and the ionization energy of group 2 metals decreases down the group because atomic radius and shielding increase, which outweighs the increase in nuclear charge, decreasing the nuclear attraction to the outer electrons. Melting points decrease down the group because atomic radius and shielding increases, which decreases the strength of metallic bonding between the metal ions, so less energy is required to overcome the metallic bonding. Group 2 metals react in a redox reaction with water to form hydroxides and hydrogen. So for example, in this equation, magnesium reacts with 2 molecules of water to form magnesium hydroxide, MgOH2, and hydrogen gas. And you can see from the oxidation numbers that magnesium goes from 0 to +2, and hydrogen goes from +1 to 0. So this is a redox reaction because both reduction, so of the hydrogen, and oxidation of the magnesium take place. The solubility of group 2 hydroxides increases down the group. So the pH of the group 2 hydroxides increases down the group because it's more alkaline as more hydroxide ions are released for the same concentration. You can see in this table, down the group, solubility and pH of the hydroxides increases. And you can be asked in exam questions to estimate the pH of a group 2 hydroxide in water. And they'll often ask you to actually compare between 2 different hydroxides. So for example, magnesium hydroxide is at the top of the group, so it's going to have a much lower pH, a less alkaline pH, closer to neutral. And barium hydroxide, much further down the group, is going to have a much higher pH because more hydroxide ions are released, so it's more alkaline. Barium hydroxide you might expect to be 13 or 14 pH. And then the uses of group 2 hydroxides. So magnesium hydroxide, also known as milk of magnesia, is actually used to neutralize excess hydrochloric acid in the stomach, which helps to cure indigestion, and are also known as antacids. And then calcium hydroxide is used to neutralize acidic soils in agriculture. So we've got a question. Write an equation for and identify the oxidation numbers in the reaction in which magnesium hydroxide neutralizes excess hydrochloric acid in the stomach. So magnesium hydroxide is going to react with HCl to form a salt, magnesium chloride, and it's also going to form water as it's a neutralization reaction. And then to balance, we need 2 molecules of HCl, and we also need 2 molecules of water. And then don't forget your state symbols. And then the oxidation numbers. So chlorine in HCl is going to be -1, and hydrogen is going to be +1. And then magnesium is going to be +2 in magnesium hydroxide, because oxygen is going to be -2 and hydrogen is going to be +1. So that gives an overall of 0 for both compounds. And then in magnesium chloride, magnesium is going to stay as +2 and chlorine is going to stay as -1. And then hydrogen in water is going to be +1 and oxygen is, as usual, -2. So you can see that's not a redox reaction, so there's no change in oxidation numbers. Acidified barium nitrate is used to test for the presence of sulfate ions, SO4 2-. Barium sulfate, a white precipitate, forms, so BaSO4. The solution is acidified to remove any carbonate ions, which would result in the formation of a white precipitate. So we've got a question. Write the ionic equation for the formation of barium sulfate precipitate in the sulfate test. In this ionic equation, we're forming barium sulfate from barium nitrate, which is made up of barium 2+ and NO3- ions. We're reacting it with a sulfate, which has SO4 2- ions. So we need to identify all of our spectator ions and remove them. So you can see that NO3- is on both sides, so we can cancel them. And that leaves us with Ba2 plus SO4 2 minus, forming barium sulfate, which is going to be a solid precipitate, and these are both aqueous ions. Okay, so we've got an exam question. This question is about reactions and uses of weak acids, methanoic acid and ethanoic acid. A student adds magnesium metal to an aqueous solution of ethanoic acid, CH3COH. A redox reaction takes place. Write the overall equation for this reaction and explain in terms of oxidation numbers which element has been oxidized and which element has been reduced. Magnesium is going to react with ethanoic acid to form a salt, which is going to be magnesium ethanoate. And magnesium ions have a charge of 2+, and ethanoate ions have a charge of 1-. So we're going to need 2 ethanoate ions for each magnesium ion. And we're going to form hydrogen. And to balance, we need 2 ethanoic acid molecules. So if we have a look at what could be changing oxidation number, magnesium is going from an element on its own to an ion. So it's going to be oxidized from 0 in energy to +2 in magnesium ethanoate. And then hydrogen has been reduced from +1 in ethanoic acid to 0 in hydrogen. In the halogens, electronegativity decreases down the group because shielding and atomic radius increases down the group as new energy levels are added, and boiling point increases down the group because the molecules have more electrons, meaning stronger London forces which require more energy to overcome. So you can see that we've got a table laying out the halogens, the number of electrons, the boiling point, and the state and appearance at room temperature and pressure of each of the halogens. So fluorine has 9 electrons in each molecule and has a boiling point of -188 degrees Celsius. And then you can see that iodine has 53 electrons and has a boiling point of +184 degrees Celsius. So you can see that as the electrons increase, there's a trend of increasing boiling point. And then at room temperature and pressure, fluorine is a pale yellow gas. Chlorine is a pale green gas. Bromine is a red-brown liquid because it has a higher boiling point. And iodine is a shiny grey-black solid because it has a very high boiling point. The halogens have 7 electrons in their outer shell, so need to gain 1 electron to achieve the octet rule, which is 8 electrons. So they form 1- ions. So for example, chlorine gains 2 electrons to form 2 Cl- ions, so 1- ions. So each atom gains 1 electron. And then there's a trend in reactivity. So reactivity actually decreases down the group because shielding and atomic radius increases, which decreases the nuclear attraction to the outer shell electrons. So more energy is required to gain an electron and be reduced. So they actually become weaker oxidizing agents down the group. Remember your definition of an oxidizing agent. So it's the element that is reduced, so it gains electrons from the element that is oxidized. We have an equation to represent this. So chlorine reacts with bromide ions to form chloride ions and bromine. So chlorine displaces the bromide ions. So it starts off as pale green as chlorine is dissolved in aqueous solution, and then it goes to orange as bromine is dissolved in aqueous solution. So you can see that chlorine in aqueous solution is pale green, bromine is orange, as we know from the bromine test for alkenes, and iodine is brown. And then in cyclohexane, it's also important to remember that iodine appears violet in cyclohexane, which can help to differentiate better between bromine and iodine, because chlorine and bromine both appear the same as they do in water. In cyclohexane, we have some precipitation reactions. So Ag+ or silver ions are used to test for halides. Silver halides form when silver nitrate is added to aqueous halide ions. So we've got an ionic equation to represent this. So Ag+ aqueous reacts with X-, which just represents any halide ion, forming AgX, which is a solid precipitate. And then we can use this to differentiate between the halide ions. So for Cl- we form a white precipitate, for bromide we form a cream precipitate, and for iodide we form a yellow precipitate. And to help us really differentiate between these precipitates, because they can be difficult to tell apart, especially silver chloride and silver bromide. So we use different concentrations of ammonia. Silver chloride is soluble in dilute ammonia. Silver bromide is soluble in concentrated ammonia. Silver iodide is actually insoluble in concentrated ammonia. So we have some uses of chlorine. So chlorine dissolves in water to form hydrochloric acid and chloric 1 acid. So that 1 represents the oxidation number of the chlorine atom in the chloric acid. Chloric 1 acid is actually HClO, and this reaction occurs by disproportionation. So make sure to check out my redox and oxidation numbers video in the top right hand corner for more help on disproportionation. So you can see in this equation, chlorine goes from 0 to -1 and +1. in HClO. So disproportionation is when chlorine is both oxidized and reduced. So it's reduced to -1 in HCl and it's oxidized to +1 in HClO. An advantage of this use of chlorine is that HClO is an oxidizing agent, so it ensures that water is drinkable by killing the bacteria, but it has some disadvantages as well. Chlorine is actually toxic, and chlorine can react to form chlorinated hydrocarbons, which are known carcinogens, so they can actually cause cancer. Then with bleach manufacturing, so chlorine reacts with cold dilute sodium hydroxide in a disproportionation reaction to form bleach, which is sodium chlorate 1. So again, that chlorine atom has an oxidation number of +1. And you can see that we have an equation. So chlorine reacts with 2 molecules of NaOH to form sodium chloride and sodium chlorate 1, as well as water. And chlorine goes from 0 in Cl2 to -1 in NaCl and +1 in NaClO, so it's disproportionation. This question is about the halogen group of elements and some of their compounds. The halogens show trends in their properties down the group. The boiling points of 3 halogens are shown below. Explain why the halogens show this trend in boiling points. So this is an easy 3 marks if you know how to answer it. So down the group, the number of electrons in the halogens increases. So because the number of electrons increases, the strength of the London forces down the group increases. And therefore the London forces require more energy to overcome down the group. Iodine can be used for small-scale purification of drinking water. Iodine reacts with water as shown below. So iodine reacts with water to form hydrogen iodide and HIO. Using oxidation numbers, explain why this reaction is a disproportionation. If we write out the equation down here, you can see that iodine starts at 0 and goes to -1 in HI and +1 in HIO, because oxygen is going to be -2 and hydrogen is going to be +1. So to balance that out, we need +1 on the iodine to give us 0. So in our answer, we can say that iodine goes from 0 in I2 to -1 in HI, which is reduction. And it also goes from 0 in I2 to +1 in HIO, which is oxidation. So the same element is both oxidized and reduced at the same time. This is how you test for ions present in samples so that we can identify the compounds present in samples. So we can test for anions, and the order that we test for anions in is we first test carbonate ions, we then test sulfate ions, and we then test halide ions or X-. And we do it in a specific order for a reason which I'll explain later. To test for carbonate ions, we add a dilute strong acid such as nitric acid to a sample. Consider why we wouldn't add hydrochloric acid or sulfuric acid. In the presence of carbonate ions, carbon dioxide gas bubbles will form, or this is also known as effervescence. And you can see in this equation how CO2 forms. So we add that acid and that provides the H+ ions, and they react with the carbonate ions to form CO2 and H2O. And then we can complete the test by bubbling the CO2 gas through lime water. And in the presence of CO2, the lime water turns cloudy because calcium carbonate precipitate forms. And then to test for sulfate ions, or SO42-, we need to add barium 2+ ions, which we can gain from barium nitrate. Consider why we might not add barium chloride. So the ionic equation for this reaction is barium 2+ plus SO42- forms barium sulfate, which is a solid white precipitate, and that is the positive test for sulfate ions. And then to test for halide ions, we need to add silver nitrate or AgNO3, and this provides silver ions, Ag+ ions, which react with the halide ions present in a sample. And if there's chloride ions present, a white precipitate forms. If there's bromide ions present, a cream precipitate forms. And if there's iodide ions present, a yellow precipitate forms. And these precipitates' colours can be quite difficult to differentiate. So to improve the test, we can differentiate by the solubility of the precipitates in ammonia. Silver chloride is the most soluble because it's soluble in dilute ammonia. Silver bromide is the second most soluble because it's soluble in concentrated ammonia, but it's insoluble in dilute ammonia. And then silver iodide is the most insoluble because it's insoluble even in concentrated ammonia and certainly in dilute ammonia. And then you have the ionic equation for this reaction. So Ag+ reacts with X-, so halide ion, to form AgX, which is a solid precipitate. So we have to do the test in this order so that we don't gain false positive tests. So for example, if you were to add barium nitrate to a compound containing carbonate, barium carbonate would form, and that would form a white precipitate, which would lead to a false positive test for sulfate ions. We can't use HCl or H2SO4 or barium chloride because these would add chloride ions for HCl and barium chloride, and in the case of sulfuric acid, it would add sulfate ions. And this would lead to false positive tests, as we'd be adding these ions into the samples that we're testing for. So we have to use barium nitrate and nitric acid rather than HCl. Testing for cations. Later in the specification, we talk about testing for transition metals. But for the moment, the only cation that we need to know about is ammonium ions, and these are NH4+ ions. And we can test for these by adding aqueous sodium hydroxide and heating gently. And you can see this ionic equation. Hydroxide ions added to ammonium ions form ammonia gas and H2O liquid. So we can then test the gas formed using damp litmus paper, so we can hold it over the end of the test tube as we heat it. And if the sample contains ammonium ions, NH4+, so NH3 gas is formed, the litmus paper will turn blue because ammonia is a base. So you've got an exam question. The first question is about electron configurations. So if you haven't seen my electron configurations video, or you need any help with electron configurations, make sure to check out my video in the top right hand corner on that topic. So they're asking us for the electron configuration of a bromide ion. So that's important. If we're forming a bromide ion, that's Br-, and that means that we've gained an extra electron. So if we have a look at the periodic table, we can see that bromine is in the p block. The bromine atom has 5 electrons in the p subshell, but since we're gaining an extra electron, we're going to have 6 electrons in the p subshell. So the electron configuration is going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, remembering that 4s fills before 3d, 3d10, and then bromine is in the 4th period, so it's going to have its outer electrons in the 4p subshell, so it's 4p6 because that's a full 4p subshell. A student adds a small volume of aqueous silver nitrate to an aqueous solution of bromide ions in a test tube. The student then adds a similar volume of dilute aqueous ammonia to the same test tube. Describe what the student would see in the test tube after the addition of aqueous ammonia. So when we add Ag+ ions in the form of silver nitrate to the bromide ions, it's going to form a cream precipitate, and this cream precipitate is not going to be soluble in dilute ammonia, so we're going to be left with a cream precipitate. It's only soluble in concentrated ammonia. Write an ionic equation for any precipitation reaction which occurs in the student's test. Include state symbols. So that's the key bit, make sure you include state symbols. And we're adding aqueous silver ions to aqueous bromide ions to form solid silver bromide. So what is the definition of enthalpy? We represent enthalpy as H, and it's the thermal energy stored in a system. Enthalpy change is measured heat energy change, usually under standard conditions, which are 1 atmosphere for pressure, 298 Kelvin for temperature, which is 25 degrees Celsius, and 1 mole per dm cubed for concentration. And standard states are the state of a substance under standard conditions. So for example, the standard state of water is liquid. We have some definitions that we need to memorize, and the first definition is the enthalpy change of reaction, and this is the enthalpy change when a reaction takes place in the molar quantities shown in a chemical equation. So for example, if hydrogen reacts with chlorine, it forms 2 moles of HCl. And the enthalpy change of this reaction is measured when it occurs in the molar quantities shown in the chemical equation. Then enthalpy change of formation is the enthalpy change when 1 mole of a compound is formed from its constituent elements. So for example, hydrogen and half a mole of oxygen react to form 1 mole of H2O. Enthalpy change of combustion is the enthalpy change when 1 mole of a substance is completely burnt in oxygen. So for example, ethane reacts with 3.5 moles of oxygen in combustion to form 2 moles of CO2 and 3 moles of H2O. And that is complete combustion because only carbon dioxide and water are formed. Enthalpy change of neutralization is the enthalpy change when an acid reacts with a base to form 1 mole of H2O. So for example, hydrochloric acid reacts with sodium hydroxide to form a salt, sodium chloride, and water, and it has to be 1 mole of water formed. So exothermic and endothermic reactions. Exothermic reactions release energy to the surroundings, so the enthalpy change is negative. So you can see that in this combustion reaction, and it's important to note that combustion reactions are always exothermic because they release energy to the surroundings, the enthalpy decreases from the reactants, so CH4 and 2 moles of oxygen, to the products, so CO2 and 2 moles of H2O. So that gives a negative enthalpy change. And the activation energy is shown at the top, and I'll give you the definition for that in just a second. Endothermic reactions take energy in from the surroundings, so the enthalpy change is positive. So you can see that in this enthalpy profile diagram, the enthalpy increases from the reactants to the products as energy is taken in from the surroundings, and it has a very large activation energy because the activation energy is the enthalpy change and it goes above that as well. You can see I've also drawn EC, which is the enthalpy change with a catalyst. So you can see how a catalyst actually decreases activation energy. Activation energy is defined as the minimum energy required for a reaction to take place. And it's important to know that it's always positive. We can calculate the enthalpy change of a reaction by subtracting the sum of the bond enthalpy of the reactants by the sum of the bond enthalpy of the products. So we have a definition here, which is the average bond enthalpy. And this is the energy required to break 1 mole of specified bond type in a gaseous molecule. And this is an average of the different chemical environments the bond exists in, because the strength of bonds varies in different chemical environments. So for example, the strength of a carbon-carbon double bond might vary depending on the different bonds and different atoms around the carbon-carbon double bond. Note that bond breaking is endothermic, because it requires energy from the surroundings, and bond making is exothermic because it releases energy to the surroundings. So we've got a question. Feel free to go ahead and try to answer it, and then you can watch for your answer. Hydrogen reacts with chlorine to form hydrogen chloride, HCl. So you can see in this reaction, hydrogen and chlorine, 1 mole of each, react to form 2 moles of HCl. And the enthalpy change is negative, it's minus 184 kilojoules per mole. Table 3.1 shows bond enthalpies. We've got the hydrogen bond, which is positive 436 kilojoules per mole. And we've got the chlorine bond, which is positive 243 kilojoules per mole. Calculate the bond enthalpy for the hydrogen-chlorine bond from the information above. So let's write out our equation for calculating the enthalpy change. And that means that minus 184 is equal to positive 436 plus positive 243 minus 2 of the hydrogen chloride bond. So then if we add 436 to 243, that gives us 679. So then we can subtract 679 from minus 184 to remove the 679 on the right. That means that minus 2x is equal to minus 863. So if we divide that by 2, that gives us minus 431.5, which is equal to minus x. So then bond enthalpy is positive 431.5. If you think about it, bond enthalpies must always be positive because they must be endothermic, because they require energy from the surroundings. So they take in energy. Calorimetry is defined as measuring the amount of heat given off or taken in during a chemical reaction. And we use this formula, Q equals mc delta T, to find the heat change in a reaction, which we can then go on to use to find the enthalpy change. And Q represents the heat change, which is measured in joules. M represents the mass of the substance in grams. C is the specific heat capacity, which is given on the datasheet and is 4.18. And delta T is the temperature change, which we can measure in either degrees Celsius or Kelvin. Okay, so I've got a question here. Magnesium reacts with aqueous silver nitrate as in equation 23.1. So magnesium reacts with 2 moles of silver nitrate to form silver and magnesium nitrate. The student carries out an experiment to determine the enthalpy change of this reaction. So define the enthalpy change of a reaction, and that is the enthalpy change when a reaction occurs in the molar quantities shown in the chemical equation. We can use that to help us answer this question. The student adds 25 centimeters cubed of 0.512 mole per dm cubed of silver nitrate. So we can use that to find the moles of silver nitrate using the equation moles equals concentration times volume. The student measures the temperature of the solution. The student adds a small spatula measure of magnesium powder, stirs the mixture, and records the maximum temperature. Temperature readings are an initial temperature of 19.5 degrees Celsius and a maximum temperature of 47.5 degrees Celsius. So we can use that to find the temperature change. And notice that the temperature increases. So this is going to be an exothermic reaction as energy is released to the surroundings. So we can immediately go to the answer line and put a minus sign because exothermic reactions always have a negative enthalpy change. So they're asking us to calculate the enthalpy change in kilojoules per mole for the reaction shown in equation 23.1. We need to give the answer to an appropriate number of significant figures. So if you have a look at the question, we can see that all the numbers are given to 3 significant figures. So that's the number we need to give it to in our answer. Assume that the density and specific heat capacity of the solution are the same as for water. So density of water is 1 gram per centimeter cubed, and the specific heat capacity is 4.18, and that all of the aqueous silver nitrate has reacted. So we can assume that silver nitrate is the limiting reactant. So we first want to use the equation Q equals mc delta T to find the energy released in the reaction. And we have 25 centimeters cubed of silver nitrate, and that means that we have 25 grams of solution because for each centimeter cubed, it weighs 1 gram, as we're assuming it's the same mass as water. And the specific heat capacity of water is 4.18, and the temperature change is 47.5 minus 19.5, which is 28, which gives us an energy released of 2,926 joules. And then if we look at our answer line, we can see that the units are kilojoules per mole. So we need to convert to kilojoules. So we divide the joules value by 1000, which gives us 2.926 kilojoules. And then we need to find the moles of silver nitrate, because if you look at the answer line, the units are kilojoules per mole. So we need to divide the kilojoules by the amount of mole to get the enthalpy change value. So we use our equation N equals CV, and that is 25 divided by 1000 converts to decimeters cubed, multiplied by 0.512 mole per dm cubed, which gives us 0.0128 mole. So then if we divide 2.926 kilojoules by 0.0128 mole, that gives us 228.5. But then notice in the equation that we have 2 moles of silver nitrate, and we're calculating the enthalpy change of reaction. So we need to do it for the molar quantities shown in the chemical equation. So we multiply 228.5 by 2, which gives us 457.1, which to 3 significant figures is minus 457 kilojoules per mole. So these questions can be quite difficult to identify what numbers you should use in your calculations. But if you read the questions carefully and decipher the information they've given you, they usually give you a clue at the end, like assuming the density and specific heat capacity as they have in this question, which can help you to make sure that you're using the right numbers in the right way in your calculations. Always check the molar quantities in the equation and make sure you define the type of enthalpy change that they've asked you to calculate. So for example, if it's enthalpy change of formation, it's going to be to form 1 mole of the product rather than say 2 mole. And that can really help you to get the right answer in your calculation. My main tip is to always check that you use the right sign. So if the temperature is increasing, it's always going to be negative because it's going to be exothermic. Whereas if the temperature is decreasing, it's going to be positive because it's going to be an endothermic reaction. Hess's law says that the enthalpy change for a chemical reaction is independent of the route taken. And this means that if a reaction can occur by 2 routes, the enthalpy change of each route will be the same. So for example, in respiration, glucose goes to ethanol and carbon dioxide, and this reaction can occur by the first route, which is the normal route, and another route, which is the combustion route. And you can see that in this diagram, route 1 is equal to route 2. And this is essentially what Hess's law means, that if a reaction can take place by more than one route, then each route will have the same enthalpy change value. When you're drawing Hess cycles, you must use the data given in the questions to help you decide which type of cycle to draw. There are 2 types, combustion or formation. Combustion cycles look like this, with the arrows facing downwards, and carbon dioxide and H2O at the bottom of the cycle. From the reactants to the products, you have the enthalpy change of reaction, and then from the reactants and the products to the carbon dioxide and water, you have the enthalpy changes of combustion values, which will be given to you in the question. For formation cycles, you have the arrows facing upwards. So from the elements to the reactants and the products, you have the enthalpy change of formation values, and then from the reactants to the products, you have the enthalpy change of reaction value. So we've got an exam question. Enthalpy changes of formation can be determined indirectly from standard enthalpy changes of combustion. 3 enthalpy changes of combustion are shown below. So we've got the enthalpy change of combustion of carbon, hydrogen and nonane, and the equation that represents the enthalpy change of formation of nonane is shown below. Calculate the standard enthalpy change of formation of nonane. So remember the definition of the enthalpy change of formation. It's the enthalpy change when 1 mole of a compound is formed from its constituent elements. So we're forming 1 mole of nonane from its elements. So we need to draw a combustion cycle because we have been given combustion values in the question. So that means that we need to have downward arrows. And on this first arrow on the left, because we have 9 carbon atoms in the equation, we need to multiply minus 394, which is the enthalpy change of combustion of carbon, by 9. And we need to multiply minus 286 by 10, because we have 10 moles of hydrogen. And we need to add these values to give us our enthalpy change of combustion for this arrow, which gives us minus 6,406. For the second arrow on the right, we have 1 mole of nonane, and the enthalpy change of combustion of nonane is minus 6,125 kilojoules per mole. So we just need to write minus 6,125. Then, if you look at these arrows, you can see that to find the enthalpy change of formation, which is this arrow up here, which is also the enthalpy change of reaction, we need to go with this first arrow on the left here, and we're going against this arrow on the right. So that means that we need to keep the sign of the arrow on the left. So that means we still have minus 6,406. And we need to flip or change the arrow on the right to positive 6,125 to find the enthalpy change of formation. So that's minus 6,406 plus 6,125, which is minus 281 kilojoules per mole. Now we have a different question. Ammonia is used to make nitric acid. The first stage of the reaction is shown below. So we have 4 moles of ammonia reacting with 5 moles of oxygen to form 4 moles of nitrous oxide and 6 moles of water. We've already been given the enthalpy change of the reaction, which is exothermic because it's negative, and it's minus 908 kilojoules per mole. Standard enthalpy changes of formation, delta HF, are given in the table. So we have the enthalpy changes of formation of ammonia, oxygen, and water. Calculate the standard enthalpy change of formation for NO. We need to give the answer as a whole number. So we can start by drawing a cycle. And note that we've been given enthalpy change of formation values, so the arrows need to go upwards. Then we can label the enthalpy change of reaction, which is minus 908 kilojoules per mole. And to find the enthalpy change of formation of the left arrow, the first arrow, we need to times minus 46 by 4, because we have 4 moles of ammonia. And because oxygen is an element, it doesn't have an enthalpy change of formation, so we don't need to worry about oxygen. On the right, we have 6 moles of water, so that's 6 times minus 242, and we're going to add it to 4 of the enthalpy changes of formation of nitrous oxide, which we don't know yet, so that's our unknown value. So minus 46 times 4 is minus 184. And 6 times minus 242 is minus 1452. Then, note the direction of the arrows. So for the enthalpy change on the top of the cycle, we're going to have to go with the arrow on the right and against the arrow on the left. So we're going with this arrow and against this arrow. So that means that we need to change the sign on the left-hand arrow, which we're going against, to positive, and the arrow on the left, the values for enthalpy change of formation on that arrow will stay as negative. So we can write this out as an equation. So minus 908 is going to be equal to minus 1452 plus 4x, which we know is going to be negative, plus 184. So minus 1452 plus 184 is minus 1268. So then we can add 1268 to each side of the equation, which is 360. So 360 is equal to 4x. That means that if we divide 360 by 4, we get 90. So the value of x, or the value of the enthalpy change of formation of NO, is going to be 90 kilojoules per mole. Collision theory. So for a reaction to take place, particles must collide with enough energy to overcome the activation energy, which we represent as the EA, and collide in the correct orientation. So you can see that here we've got ammonia reacting with H+ ions, and when the lone pair on the nitrogen atom aligns with the H+ ion, then they can react to form ammonium ions, NH4+. But if the lone pair is facing away from the H+ ions and they collide, they won't react, and so reactions won't take place if they're not in the correct orientation. So the Boltzmann distribution is a concept that we use to represent the energy of molecules in a reaction system. On the y-axis we have the number of molecules in the system, and on the x-axis we have the energy of the molecules. And you can see that the area under the curve is the total number of molecules. And the area to the right of the line, which is represented as the activation energy, or EA, is the molecules which can react if they collide in the correct orientation. The Boltzmann distribution always starts at the origin, 0, 0, because 0 molecules have 0 energy. And then it can never touch the x-axis after the origin, because the molecules cannot have 0 energy. We can determine the effects of different conditions on the Boltzmann distribution. So for example, if we increase the temperature, then more molecules are going to have a higher energy. So this means that a larger proportion of the molecules have an energy higher than the activation energy, so they can react upon collision in the correct orientation. So you can see that this line for the higher temp is lower at the start and higher at the end, because a larger proportion of the molecules have more energy. For an increased concentration, we have the same gradient, but we simply have a higher line, which means that more molecules have higher than the activation energy, so can react upon collision in the correct orientation. Catalysts also have effect on the Boltzmann distribution. So the activation energy shifts to the left. As you can see, EC here represents the activation energy in the presence of a catalyst, and this means that a larger proportion of the reactant molecules have the activation energy. So we can determine the rate of reaction using this equation. So the rate is equal to the change in concentration over time. And the units that we use for rate is mole per dm cubed per second, because the change in concentration is measured in mole per dm cubed and the time is of course measured in seconds. So there's some important factors affecting the rate of reaction. So we've got catalysts. So as you can see in this diagram, the activation energy in the presence of a catalyst is decreased because catalysts find an alternative reaction pathway without themselves being used up. There's two types of catalysts. Homogeneous catalysts, which are in the same physical state as reactants. So they react to form an intermediate and are regenerated. So for example, phosphoric acid in the hydration of alkenes. And then we have heterogeneous catalysts, which have a different physical state from the reactants, and are usually solid. And the reactants adsorb, which means they weakly bond to the surface of the catalyst. Then they desorb. So for example, platinum in catalytic converters is a heterogeneous catalyst, because nitrogen monoxide and carbon monoxide adsorb to the surface of the catalyst, react to form nitrogen and carbon dioxide, and then desorb, so leave the surface of the catalyst. So there's some important benefits of catalysts in industry. They mean a lower demand for fossil fuels because there's reduced energy use, which means lower costs as well. We can calculate the rate of reaction using continuous monitoring, which is recording the amount of a reactant or a product at regular time intervals. And we can do this by three main methods: gas collection, using a gas syringe, and we measure the volume of gas formed; mass loss, where we use a mass balance to measure the mass as a gas forms. So as a gas evolves, it leaves the reaction mixture and that decreases the mass. And then we have calorimetry as well, which is where the concentration change is monitored by measuring the absorbance of light by a sample. So what a colorimeter does is it shines light through a sample and it measures how much light is absorbed by the sample. So the higher concentration of a sample, the higher the absorbance will be. So rate graphs, we can use tangents to calculate the rate of a curved graph, and the gradient of the graph is equal to the rate. So as you can see, the change in y divided by the change in x means the change in concentration divided by the time, which is equal to the rate. So we've got an exam question. Using the Boltzmann distribution model, explain how the rate of reaction is affected by temperature. You're provided with the axes below, which should be labelled. So that's important. We need to remember to label the axis. So on the y-axis, remember, we have the number of molecules. And on the x-axis, we have the energy. And then a Boltzmann distribution, we know always starts at 0, 0, so the origin. And it increases like this, and then peaks and decreases. As the number of molecules increases, the energy decreases. So that's our lower temperature. And then we can draw a Boltzmann distribution for a higher temperature. So it's lower at the start and higher at the end. And then we want to label our activation energy, or EA. So we can see that a large proportion of the reactant molecules will react upon collision in the correct orientation because they have the required EA, or activation energy. So in chemical equilibriums, reversible reactions are represented by the equilibrium symbol, as you can see here. So in this equilibrium, ethanoic acid is dissociating to H plus and CH3CO minus ethanoate ions. And in a dynamic equilibrium, we have certain conditions which are maintained. So there is constant concentrations of reactants and products. The rate of the forward reaction is equal to the rate of the reverse reaction, and it's in a closed system, which means that the conditions are constant and there's nothing added or removed from the reaction mixture. Le Chatelier's principle says that if the reaction conditions of a dynamic equilibrium are changed, the equilibrium will shift to favour either the forward or the reverse reaction in order to oppose the change. So when you're thinking about the effects of changing conditions on Le Chatelier's principle and therefore the position of equilibrium, you need to think, what opposes the change? The effect of a change in temperature depends on whether the forward reaction is exothermic or endothermic. So we know that exothermic reactions release energy to their surroundings, and endothermic reactions take energy in from their surroundings. So exothermic reactions increase the temperature of their surroundings, and endothermic reactions decrease the temperature of their surroundings. If the forward reaction is exothermic, this means that the reverse reaction is endothermic. So for example, in this exothermic reaction, A plus B goes to C plus D, and the enthalpy change is minus 120 kilojoules per mole. That means that the reverse reaction is endothermic, so the enthalpy change of the reverse reaction is positive 120 kilojoules per mole. So if the temperature of this exothermic reaction is increased, the equilibrium will shift in the endothermic direction, so the reverse direction, which is to the left, so towards A and B. And oppositely, if the temperature is decreased, the equilibrium will shift in the exothermic, the forward direction, which is to the right, towards C and D. And this is because the equilibrium shifts to counteract the change. So in the case of increasing the temperature, the equilibrium shifts left to decrease the temperature, because the endothermic reactions take in energy from the surroundings and decrease the temperature of their surroundings. To oppose the change, to decrease the temperature. So changes in concentration. Increasing the reactant concentration causes the equilibrium to shift towards the products to oppose the change and decrease the reactant concentration. And on the other hand, increasing product concentration causes the equilibrium to shift towards the reactants. So you have to think, what opposes this change? So for example, we've got HCl aqueous going to ammonia, forming ammonium chloride. So the question is, what would be the effect of increasing the concentration of HCl, which is a reactant, on the position of equilibrium in the reversible reaction above? Explain your answer. So if we increase the concentration of HCl, we increase the reactant concentration. So the equilibrium is going to shift to the opposite direction, to the right, towards the products, because this is going to oppose the change and increase the concentration of the products and decrease the concentration of the reactants. So for pressure, this only applies to gases. An increase in the pressure will cause the equilibrium to shift to the side with the fewest gaseous moles, because this opposes the change. If you increase the pressure and the equilibrium shifts to the side with the fewest gaseous moles, then that decreases the pressure, because you have fewer gaseous moles present. Decreasing the pressure of the system will cause equilibrium to shift to the side with more gaseous moles, opposing the change. So for example, in this reaction, we have nitrogen reacting with 3 moles of hydrogen to form 2 moles of ammonia. So on the left-hand side of the reaction, we have 1 mole of M2 and 3 moles of H2. That makes 4 moles, and on the right side we have 2 moles of NH3 ammonia. Catalysts don't affect the position of equilibrium, but they instead just increase the rate of reaction for both directions, so both the forward and the reverse. So that means the equilibrium is established faster. So we've got a new concept here, which is the equilibrium constant, which we refer to as Kc. And Kc numerically indicates the position of equilibrium, and it is the ratio of the concentrations of the products to the reactants. When we put a reactant or product in square brackets, that indicates the concentration of the reactant or product. So in Kc expressions, we have the concentration of the products divided by the concentration of the reactants to the power of the moles or the stoichiometry of each. So for example, in the general reaction, A plus 2B goes to D plus 2E. A and B go on the bottom as reactants, and D and E go on the top as products. When we have a balancing number in front of any of the reactants or products, we put that as a power to the concentration of that reactant or product. So for example, we have 2B, so that means we do B squared, and we have 2E, so that means we do E squared. The units of Kc vary depending on how many species take part in the reaction and the stoichiometry of the reaction. So for example, in the reaction above, we have A plus 2B going to D plus 2E. And for each reactant and product, we have mole per dm cubed. So on the top of the equation, we have mole per dm cubed to the power of 3. And on the bottom, we have mole per dm cubed to the power of 3. So both of these units cancel out, and that leaves us with no units. It can sometimes be more difficult to calculate the units. So for example, in this reaction, we have 2 mole per dm cubed on the top and 3 mole per dm cubed on the bottom. So we cancel out the top, and that leaves us with 1 on the bottom. And then because it's on the bottom, we have to do the inverse of it, so we have to change the symbol, and that becomes mole to the minus 1 dm cubed, but we usually put it in the positive order first, then the negative. So that's dm cubed per mole to the minus 1. So when Kc is equal to 1, that means that the equilibrium is exactly halfway between the reactants and the products. When Kc is more than 1, that means the equilibrium is shifted further to the right, so the products are favoured. And inversely, when Kc is less than 1, that means that the equilibrium is further to the left, or the reactants are favoured. So we've got an exam question. This question is about ammonia. In industry, ammonia is made from nitrogen and hydrogen. This is a reversible reaction as shown in equilibrium 24.1. So we've got 2 nitrogen reacting with 3 hydrogen to form 2 ammonia. And you'll notice the enthalpy change is exothermic. It's minus 92 kilojoules per mole. Explain how Le Chatelier's principle can be used to predict the conditions of temperature and pressure for a maximum equilibrium yield of ammonia. So let's deal with temperature first. So the forward reaction is exothermic. That means the reverse reaction is endothermic. So we're going to want to decrease the temperature to shift the equilibrium to the right, because exothermic reactions release energy to their surroundings. So if we decrease the temperature, then the exothermic direction will be favoured, because the equilibrium will shift to oppose a change to increase the temperature. And then for pressure, you'll notice we have 2 gaseous moles of ammonia on the right, and we have 4 gaseous moles of nitrogen and hydrogen on the left. So to shift the equilibrium to the right, we're going to want to increase the pressure, because if we increase the pressure, the equilibrium will shift to the right to counteract the change and decrease the pressure. Now you might be asked in exam questions to justify why these optimum conditions might not be used in industry, and this is often for high temperature because it can be expensive and have high energy requirements to maintain, and the high pressure can be dangerous. Using certain conditions, equilibrium 24.1 has the equilibrium concentrations in the table, and they're asking us to calculate the numerical value for Kc under these conditions. Give your answer to an appropriate number of sig fig and in standard form. So the appropriate sig fig is going to be 3 significant figures, because in the table in the question, we're given all of the concentrations to 3 significant figures, and then we need to remember to leave it in standard form. So remembering that the formula for the Kc is the concentration of the products divided by the concentration of the reactants. So our product is ammonia, so that's going to be 0.862 mole per dm cubed. Not forgetting that we need to square it, because in the equation, remember, we have 2 moles of ammonia, and then we need to divide it by concentration of nitrogen, which is 1.25 mole per dm cubed, and that's just the power of 1, and then we have hydrogen, which is going to be 2.75 to the power of 3. And then if you put that into the calculator, you get 0.02858. And then you convert to 3 significant figures and standard forms. That's 2.86 times 10 to the minus 2. Thanks for watching. Make sure to check out my amount of substance revision video, which should be in the bottom right hand corner now. You can also check out my website, which will be in the description below, in order to purchase my notes and flashcards.